All right, I promised two different ways in which resonance is applied, and now we're going to hit, we've seen number one, but let's see 2 and 3. Number 2 looks very much like number 1. Remember, in number 1, just to peek back, we started with something like this. For number 2, we're just going to show two bonds that are double bonded to each other. Remember, again, resonance involves the spreading out of electron density in p orbitals and pi bonds. So we at least have, in this model, we have two atoms that are connected by a double bond, and that this second bond is a pi bond. So how are we going to spread out this electron density? Well, we need our double-headed arrow, that's our resonance arrow. And what we'll do is we'll simply break this pi bond and move those electrons to atom A. I could have just as easily shown the electrons going to atom B as well. Now, once we break that bond, we're only going to have one bond between atom A and B, and based on the way that I've shown this electron movement arrow, those electrons end up on A. Well, if you go through this mathematically, what's happened with the formal charge? A now has a negative charge, and B has a positive formal charge. So these are our two resonance forms that we can draw under this second model. Note that we didn't involve a neighboring atom with a lone pair. We just said if anytime you have a double bond, you can break the double bond, put the electrons on either atom. I've chosen atom A in this case. So which one of these two forms, these two resonance forms, having a hard time with resonance, two resonance forms, which of these is better? Remember, these are two Lewis dot structure representations of the same structure. They just have a different electronic rearrangement. Well, I'd favor this one. I think this is going to be the more stable, and we call this the major contributor. But that doesn't mean that there's none of this minor contributor contributing to the picture of the reactivity of the structure. So these are two different resonance forms. Yes, I like this one better, and it follows the rules of the Lewis dot structures better. There are no formal charges. Hopefully everything has a full octet. And then the minor contributor starts to violate some of these Lewis rules, but it still could play a role in the reactivity of this structure. Again, this is a little bit abstract at this point. We're going to see specific applications of this that will hopefully help you understand some of this terminology. So what's our third application of resonance? This is, I would say, uncommon. Our first one was common, really common, like the most common. And then number 3, I'd say, is rare. So number 3, we'll have atoms that are, again, double bonded to each other. And then we'll have another atom that has a vacant p orbital. You don't see vacant p orbitals too often, and when you do, typically it's for a carbocation. That may be, in fact, the only reason that we'll see one in this class. So what happens? We're going to do a resonance form of this structure. We're going to move our electron density. We're going to start with our pi bond. We're going to move this bonding pair of electrons. We're going to move this to make a second BC bond. And we can make a new bond to this atom because this carbon has this vacant p orbital. What's this going to look like? And tell you what, let's give this C a positive charge because that's typically where you encounter it. So this carbon now is neutral, but atom A has lost electrons, has lost a bonding pair. So now it has a positive charge. And what we see is we have now drawn a new alternative Lewis representation of our original structure. One of these may or may not be more stable. It depends on the identity of the A atom. And so at this point, you might start invoking other rules. Well, is A or B more electronegative? The more electronegative atom may be less stable bearing that positive charge. But these are alternative forms. We don't have enough information in this to say which one's the major or minor. But as we draw more specific molecules, we'll be able to make statements of which is the major or minor form. Anyway, this is a rare example. Probably seems kind of weird talking about vacant orbitals because most things have a full octet and don't have vacant orbitals, at least in their valence shell. So, but it's somewhat common, and we will encounter it at times. So this completes our picture of the different scenarios in which we will encounter resonance.